effect and simultaneous of the crystallization of intercooled water droplets dispersed in an emulsion. So what you see here this is the first one. The second one is understanding the crystallization droplet dispersed in water emulsion and detect the local heating of concentrated emulsions during the water droplet crystallization process. So what you see here in the right in the figures, these are the pictures that I borrowed from the internet from the paper, who described the physical or who considered the physical measurement. This is the prototype model of the crystallization phenomenon or process, and here is the temperature. Here you see the temperature of the particles when we are making supercooling. So of course you see here that we are making supercooling, so it is decreasing. You observe that you have a decreasing strategies for different values of the temperature, different parameters. So you see here it is decreasing, decreasing. This means that you have crystallization. And at some time, you see here that at some time, the temperature becomes higher. It increases for a while. You see here the amplitude here is 4 degrees. So why this happened? What happened here? So here, what happens is when the crystallization process is in process, so particles are getting solid, and due to this interaction between particles, these particles have some energy, and when they hit together, so they produce an energy, and this makes this bump. This makes this bump here. So the idea now, this is the experiment, what the measures or the experimental or the experience showed. Now we are going to try to capture this phenomenon here, the reconstruction of this bump when this temperature is turns to be increasing. Instead it was decreasing up to some temperature, and then it becomes increasing, and then it decreases until the complete crystallization of the particles in the water. So this is the goal, this is the idea. So here just I say something about literature of existing approaches. So we have experimental approach that is based on Demas and contributors and Rafiqi and contributors also. They presented physical model in supercooled water droplets using deterministic models and have validated by the experimental data. But the models cannot detect the local heating concentrated emulsion during the water droplet crystallization process. So this is somehow our starting or our initial starting points to be interested in this. So this is the two references. And there is another reference due to Krishi, who proved the local heating phenomenon experimentally for concentrated emulsion. And it goes back to 1992. This is a PhD thesis in Pau, university in France. So now the problem modeling. So in order to describe the mathematical modeling, we assume that a total droplets in a volume V is denoted by N capital T. And these are cooled at a constant cooling rate beta. We are going to make them to apply this process of supercooling, and we denote by NC little t and little x, a proportion of this quantity in a given volume, which corresponds to the number of crystallized droplets in a controlled volume at the position x and the time t. So therefore, what we can get for this proportion of crystallized droplets, the number of particles that are crystallized within a fraction of time dt. So it can be written by the equation 1,1, which is given by this very simple equation. Of course, this is the variation of the number of droplets during a short time period. This is equal to the number of initial droplets that we have at time capital T, at time t, or for this interval 0 capital T. And this is the number of droplets at time t that I have described just before. And times some function here, gu of t, which is u is the temperature which depends on little t and xt, but I just omit the parameters here. G is what we call the nucleation probability law. Okay, now using the proportion or the fraction of crystallized of droplets phi, this is the number of droplets at time t divided by the total number of droplets that we have for this interval. And then we can rewrite just by dividing by n equation 1,1 this very simple equation. So this is a very simple equation or the deterministic model. And now what happened after this? After this, there was a theoretical approach due to Valitro, who reported a mathematical model to describe the local heating within the emulsion due to the stochastic crystallization of water droplets. Because it has been observed experimentally that there is some stochasticity in the crystallization phenomenon. And this is due to this paper in 2002, where the authors proposed a stochastic mathematical model describing the ratio of crystallized particles with this function phi, which is described by this system of PDE and SD. So these are some constants, right? And you have here some the derivative of U, which is the temperature, which is related to, which is a coupled system. As you can see here, you have the phi. I tried to write them in different colors so you can see them very explicitly. And this is the droplets that I have described. This is the corresponds to the deterministic part, and this is the stochastic part. So this is a diffusion equation, a stochastic diffusion equation in some domain D on the interval 0t, where you have some initial conditions. Okay, and of course, since this is a proportion, so it belongs to interval 0,1. Okay, so and this K is the thermal conductivity of the emulsion, and there are some constants. This Cp is the constant of heating capacity, rho is the mass density, kappa is the mass fraction of water, Lf is the latent heat of fusion. Okay. Let me, I think that I have to, let me just please stop the sharing and then again make the compilation, because I see some more questions that appeared, so I have to compile again to see the references, because it's interesting to know what we are referring to. Okay, I have to close this one. Okay, sorry. I have to close this. And then I am sorry for this short break that happened, but it will disappear. Okay, so I have to So here you can see now I will share now. Sorry. Yeah, this is the file. Okay. So then I have to put F12. F12. Okay, so the F12. Okay, so you can see my screen now, please. Okay, so in the reference one, the authors used the unknown diffusion process. I mean that the previous model, this one, this is the reference one, okay? And in this model, what they described, what they did in order to identify or to show our contribution, yeah? So the author considered the unknown diffusion term with dependent variables, the temperature and the crystallization fraction of droplet phi. This is the disadvantage of the first model. The second one is the diffusion term of the previous reference. Assume that when for new negative, U has to be greater than some given A, and phi is negative whenever, phi is greater than 1, which is not natural. So phi is a proportion, so it has to be between 0 and 1. So thirdly, in this reference, Trujillo and Vallée use the absolute value of the W. This is the increment of the Brownian motion instead and replace the W by dt, some the Brownian motion shifted by Liebig measure. They replace the W with this. Okay. So this is what they did. So other point, the disadvantage, the numerical result of this model have not been compared with the experimental results obtained in by Krishy. So this is somehow our comments or our critics to the previous work. Okay, so now the strategy to tackle this problem is stochastic models have to describe in the crystallization droplet in water emulsion. So in our stochastic model, the term is specified and can vanish only for these situations. Outside of 0, 1, it is 0, right? There is no proportion. Okay, so our definition of the sigma, the parameter sigma that appeared in the equation, depend on 3 parameters, D, C, D, and E, which are identified with the genetic algorithms in order to fit the experimental data and detect the local heating of the concentrated emulsion. So this is the tools the parameters that will be used to calibrate the model and to try to identify this part where you have the decreasing of the temperature and you have this bump, this part that happened in the experimental analysis or the experimental measurement. So of course this is related to the existence and utility of solution of the stochastic model to describe, and then we are going to consider numerical schemes to solve this system of stochastic partial differential equations, because you have an equation with the Brownian motion and another equation which is a PDE. So this is a coupled system of PDE. And lastly, we consider numerical simulations. So this is the strategy that we are going to adopt in this paper. So we start first of all by the first part, seeing that okay, which will discuss the stochastic models of crystallization of droplets in the water. Okay, so here just I listed some of the points that that has going to be discussed. Stochastic model based on the heat energy equation and the nucleation theory with the specific drift and diffusion. Okay, so this is the techniques that we are doing. Assumptions and definitions of solution, controlling a priori estimates of discretized method, and then existence and uniqueness of the stochastic model. So I'm sorry, I will not really go in details because it goes from modeling to existence theory to a priori estimates, control of the quantities, convergences, relative compactness, and so on. So I will not really go in details in some parts here, but I will focus mainly on the applications. So the part 2 concerns numerical schemes to solve the stochastic model, experimental device and physical model in a cylinder, and then finite volume method for solving the physical model. The part 3 is the numerical results and discussions. So we make many comparisons with different parameters. We discuss first the deterministic case when the diffusion coefficient is 0. So when we take the sigma is equal to 0, everything comes deterministic. And then the second point is the stochastic case when the diffusion is not 0. The comparison between experimental and numerical temperatures, right? And then the effect of the temperature stabilization, TS. There is some temperature stabilization that has to be introduced on the crystallization of kinetic inside the emulsion. So this is the three parts of and the last one, of course, is the conclusions and perspectives. So let's get started. So this is the model. This is the sections. So I consider a domain of RD, which is open a Lipschitz domain. What do we mean by Lipschitz domain? The Lipschitz domain means that regular enough. We can replace this sentence by just saying regular enough. And the capital gamma is the boundary of the domain. So n with this arrow is just an outward unite normal of the domain D. The interval 0t, white WT is a Brownian motion, one-dimensional one, defined on a complete probability space. Capital E with the math bold stands for the expectation. FT is a filtration, a family of increasing families, sigma algebras that are generated by the Brownian motion. So here are the functional spaces, the classical functional spaces that we consider. You have H, V, and the capital H here. This is the corresponding functional spaces that we need to prove the existence. So of course, we use standard notation for lim-sup and lim-env, and consider for partial derivatives, we consider this notation, dt to indicate the derivative with respect to time. This is the derivative with space, second derivative with space. You have the norm in different spaces, the different in L2, just N0t. And here in H1, we put 1 instead of 0, and gamma t to describe this norm. So let me just make a short comment on that norm here. You observe that we are considering here the expectation because this quantity is random. This is the first observation. The main one is where you have here some weight factor, some weighting factor here to make things a little bit. This is a smoothing effect somehow, or regularizing effect. Whenever we have singularities, you will see in the application that we will have some singularity for this equation, and therefore we need to describe or to consider some norms in appropriate spaces in such a way to capture this or to overcome this difficulty of singularity. So this is our system that we are going to solve. So just we replace in this unknown coefficient here, bu phi, by this term here in the right-hand side. This is the sigma. Here is the diffusion coefficient multiplied by the complement of the crystallization proportion. The particles that are not crystallized. This is the number of particles that are not crystallized as a ratio, the ratio of crystallization. And this is, of course, the small difference between two elements. And this is our system of PID. This is, of course, a coupled system. It cannot be decoupled due to the U that you have inside here and you have U inside here. Okay. This is why it is a decoupled system. And here we specify the functions G and sigma that correspond respectively to the nucleation probability and the correction of the growth crystallization, the diffusion term. So they are described by these two forms here, and we put them to be here 0 otherwise, and here just a constant whenever U is greater or equal to. Okay, so this is as I mentioned before, the A and B, C, D, E are parameters that will be used for calibration of the genetic algorithms when we are going to identify parameters. We use this calibration in order to compare the result or to fit the model, this model with the experimental temperatures that has been collected when the measures were taken in labs. Okay. Okay, so in order to show the system equation are stable and admit a unique solution, we consider the following assumptions. So I list 3 assumptions. So we have the initial condition here, and this temperature is related to in the boundary. It has to be in that space. The function key has to be continuously Lipschitz increasing function, which satisfies these inequalities here, and it is bound. Its derivative is bounded, and phi 0 is f0 measurable. We can consider it as a deterministic function here, since the f0 is you have the 0, 1 law here, and then you can just consider deterministic functions. But it's not a problem if you consider it for in some after some t0, for example, and some t0, for example. Here you consider things starting from this point. So instead of 0, you start from t0, and you can just shift things by this constant. We have simplification here, some simplification here, just to make things very, very, very simple. We can choose this constants in such a way that we have this product to be 1. Okay, good. So now, what is the definition of the system tree for the previous system? A solution of this system is a couple of predictable processes that lies in these functional spaces, such that they satisfy this integral equation here. Okay, and the second one. This is for the PDE, and this is for the stochastic differential equation. This is the integral form of the equation. So to solve this couple of systems, we follow the following steps. So we consider these 3 points, approximating the system by Euler-Moriyama scheme, but for Hilbert-valued stochastic SDE, stochastic differential equations, due to the functional space that we have, establish a priori estimates in L2 norms, H1 norms, with the application of the well-known. So this is the tools that we use for this estimation. Etos formula is a main thing, and then Gronwall's lemma, as you know, for solving very equations. And this type of system, it appeared that it is useful to use what we call the energy estimates for a stochastic parabolic equation in order to prove existence and uniqueness theory. Okay, so this is the discretization process. So please, whenever you have any question, you can ask. Yes?
C'est pas juste.
Please, what you said?
I think it's a problem with the microphone. It's not a question.
Oh, it's not a question. Okay, good. Okay, good. So this is the discretization of the scheme, the Euler-Moriyama scheme. So we consider here the increment of the Wn is just the value of the Brown motion at diameter Tn, and Tn is just n times tau, and tau is just the step of the subdivision, or this is just capital T divided by the number of points chosen in the interval 0 capital T. And Un is just the evaluation at the temperature at time Tn and the point x. And again, phi n also is just the value of this function at time Tn, and then evaluate also at x. Okay, so we with this initial point u0 and phi naught, and then we define Un plus 1 and phi n plus 1 by this integral equation. So you see here, this is the input, the previous one, the previous ones here, and the next ones are indexed by Un plus 1, Un plus 1, phi n plus 1, Un plus 1. This is the first equation. The second one is the Euler-Moriyama for the stochastic differential equation. So you have here again phi n plus 1 in terms of phi in here, Un here, the previous one, and Un here, and just here the increment of the Brownian motion. So this is the time or the type of discretization. So this is the part of the error analysis or appropriate priori estimates. So the system for 10 and sorry, this has to be another number, 14 and for 11 here. Oh, sorry. No, the system 9 here. It has to be 9 and 10. Okay, this has to be 9. This one has to be 9. Okay. They have with property 1 an FT measurable solution. Of course, this iterative construction is, we can obviously prove that this FT adapted. It is a family of stochastic processes that are in the right spaces. So now under the assumption that we have assumed H1, H0, H1, H2, then we have this a priori estimates. So this is a class. I will not go in details in the proof, but the details of the proofs can be found in the paper if you are interested to know the details. And this is what we need. Okay, now let's go to the main result, which is the existence and uniqueness. So if we denote by this xt as the summation of this indicator functions, this is a sample functions that starts from x0. This is the notation that we use. And now, as under these assumptions, there exists a unique couple of solutions u and phi in the appropriate spaces that satisfy the equation in the sense of the definition for 1, such that phi n is v-valued and have continuous trajectories. Moreover, it is between 0 and 1, and the simple parts of the stochastic reaction field, which is u, this is the temperature, are continuous function with respect to the initial conditions, u0 and phi naught for all t. Okay, the proof of this theorem will be proved in different steps. I will just show show you the important steps that we are going to use. We need to introduce some notations here to simplify the expressions in the estimations. So we have, this is functional analysis somehow, right? This is functional analysis, and we have to prove that this sequence is bounded in the appropriate space, and it belongs, the limit belongs to this. Okay, and the sequence, sorry, not the limit so far, no. This sequence is bounded in these spaces, okay, in these two spaces. And un also is bounded in the appropriate space. The sequence of function k of n is also bounded in that space, gn and sigma n. So we have boundedness of these families in appropriate spaces. And then from the previous lemma, we can therefore extract the subsequences which will index by primed, only primed, for which we have convergence in a weak sense. So you see here the symbol of weak star. So you know, this is a functional analysis. We have to prove some convergence of spaces and then identify the limits and so on. So this is the idea of this lemma. And here are the main steps in which we have you are going to use the Ito formula for this function here, because if you remember, we put this white here in order to obtain the right space for the solution. And here we have what we call energy inequality for parabolic equation, and then we integrating the system for 10 and using the estimation of the lemma for 3, the weak convergence for all t of 0, and we have the Taylor expansion formula can be written in this way. So we have some correcting term here, some error here that described by this this parameter. Okay, so you have here this is the derivative with respect to some parameter in gamma. Here I just put some. This is L. This is the parameter moving in the boundary. Okay, this concerns the parameter moving in the boundary. Good. So this is the by the way, this is the details of the steps that has to be followed properly to prove the existence. So let me move to the existence uniqueness. Let me move to the applications. So this is a slide concerning the uniqueness. So due to the time, I have to move a little bit faster. So I consider now experimental scheme. So we have the experimental device and physical model in the cylinder and the finite volume method for solving this physical model. So the experimental prototype, this experiment consists of a metallic cylinder with the volume about 500 centimeter cube. Okay, the area contains a water emulsion. And the 2 is the lighted plugs close to it. This is like the covers of the cylinder from above and from below. The second one is the thermocouples are located uniformly in the cylinder according to the wet H and reduce R. So this means like we are trying to make a transformation of the equation with respect to T and H2 with R and some H. We transform things to cylindric parameterization. And then a metallic cylinder is immersed in a liquid solution at temperature UP, which can be heated or cooled at a constant rate R using thermostat. Okay, this is the physical experiment. And the assumptions, of course, is the thermophysical properties are supposed constant during the cooling process. These are the assumptions. The thermophysical properties are dependent on the mass friction kappa of the water droplets dispersed in the emulsion. So during the experiment, we have two effects given the heat transfer inside the emulsion. Inside the emulsion, they have something that makes heat transfers. Okay, so there is the cooling process monitored by the so-called debate temperature, which is U, and the stochastic crystallization of water droplets in emulsion media. So in order to remain under the same conditions of the experimental protocol, we assume that this H, the weight H of the cylinder, is much larger than its diameter. And then we assume this H is very large than respect to the R. So this allows us to neglect the axial effect compared to the radial effect. This is the interpretation, okay, the useful information. Then the stochastic model is obtained by using cylindrical coordinates and by noticing that the solutions are dependent only on R and T. So hence, the stochastic model now will be described by the following equation here, 716. So now you can recognize, maybe ask the question, how this is appeared now. This is why we considered, because here you have singularity, this is why we consider this weighted space with exponential minus 2R 2 gamma times T. Okay? Then this is the same stochastic equation. So now according to the experiment device, the boundary conditions complete the equation. Now we have these conditions. I don't know if I am contacted by some people saying maybe that, okay, no. Good. Okay, now let us move to the finite volume method for solving the physical equation. We have some steps here. We generate a grade by dividing the domain into small discrete control volumes, and we place the number of nodal points in the given domain where each node is surrounded by a control volume or cell, and the physical boundary coincides with the control volume boundaries. We investigate over the control volume to yield a discrete equation at its nodal point. So we use a trade-diagonal matrix algorithm. This is called the algorithm, also known as the name Thomas algorithm, to solve iteratively the set of discretized equation. So this is a reference related to the finite volume grade technique, solving one or two dimensional heat flow problems. So this is somehow the procedure. You see here that you have the domain and you have the discretized domain here, and then you have nodes. This is one node, and here this is the node. This is the edge, face, and subdomains. Okay, so let me just go a little bit forward for this. Then we integrate the system that I have described, 716, the system for which we are considering the example, and then we obtain this equation. So this is mathematics. This is integration by parts, and making different, calculating the values at different points and so on. Okay, so this is mathematics equations that we have manipulating these equations to obtain interesting objects to be able to iterate to find numerical solutions. So let me show you the numerical results and discuss what is going on. So this numerical part concerns deterministic case, sigma equal to 0, the stochastic case, sigma different, and comparison between experiment and numerical temperatures. And here also another point, which is the effect of temperature of stabilization on the crystallization kinetic inside the emulsion. So this is the parameters are chosen like this. If you remember, we have fixed the sum of parameters kappa, little a, temperature S, which is the stabilization temperature, beta, and this R. This is the radius of the cylinder. Okay, so here, this is the first results. So you see here in the deterministic model, you have here the inputs, the parameters, and the temperature, which is the base temperature here, UP, is linear in time. Okay, beta times T times some initial value, and you have here each parameter. This is temperature corresponding to R equal to 0. This is the temperature corresponding to R equal to capital R. This means that at 0, at the center, and at the border of the cylinder, right? So this is, and this U is near the cylinder wall. The blue one is near the cylinder wall. And of course, the black one is the base temperature. Good. And here you see exactly, there are some many figures here with different colors that we cannot see here. But this is what we have from the experiments, right? For the deterministic model. So this gives the temperature profile from the left. And from the right, you have the ratio of droplets, the phi, describing the proportion of particles that are crystallized. So you see here from 0 to 4 some 4 and something, you have nothing. Okay. Of course, here this is near the cylinder. This is at the center of the cylinder, and this is at the border of the cylinder for little r equal to r. Okay. Now you see here, this is of course the increase in the number of particles are increasing here, as you can see. When you arrive here, you have complete crystallization. This is the deterministic model. Let's move to other results. The stochastic case, for which sigma is different from 0 and C is 0, 1, but D and E are equal to 0. Okay, so let's see here. You see, for the stochastic model, you start to observe randomness here. Okay, so you see that you have some irregular figures here for the orange color, right? So here is the random effects appeared here, and we succeed to recognize the zone or the region where we have this bump, where we have the increase in the first point when the temperature increases, and then reconstruct the shape of the experimental measurement. Here is again, you see here clearly in the right hand side, the ratio of droplets. We cannot really observe stochasticity here. We can, if we focus more, or if we make it a little bit larger, we can observe the effect of randomness here. But this is exactly have the same shape as the previous one. Okay. Now, this is the case where we have the parameters D and E are different from 0. Okay. So you will see here that we are somehow here, you are neglecting the effect of randomness. So you see here, you don't see in this figure this irregularity points like this. You know, this irregularity points. I'm sorry that I'm just describing this by my mouse, but we cannot observe compared to the other This one is stochastic because sigma is different from 0. But what compensates here? The compensating here, this is the effect of the parameters D and E, because they are very big. So they like they are hiding the random effect. Okay. What is the comparison now? Let's make the comparison between experimental and numerical temperatures. Numerical temperature means the numerical temperature obtained by the model, and of course, experimental are the one that has been measured by Krishy in 1992. So you see here that they are very close to each other. The red line and the blue line, they are really close to each other in this part and also in this part. And you see that the BEMP is reconstructed in the same region, and it behaves exactly the same shape. Okay, so this is of course related to some other simple models described firstly by Eloitmani and collaborators, where they use the Brown emission to describe this. Okay, this is just some comments about this, but let me again go to see when modifying the mass friction, what happens if we are modifying this kappa. Okay, so we present here the output of numerical temperature U of the stochastic model that we have considered for different values of kappa. So you see here we double at each time we multiply by the first value of we add 50%. Sorry, no, we have here just okay 40, 20, 40, and 60%. So we remark that the curves have the same shape as that of the Krishy curves. We compare this by the Krishy results, and we see that exactly they have the same, they go in the same behavior here. So the results here are very satisfactory here. Good. Now the treatment of the impact of the stabilization temperature on the kinetic of crystallization inside the emulsion. Now we are going to variate the stabilization temperature, which is TS. We start by TS to be minus 40 degrees, minus 50 degrees, minus 60 degrees. And we take R equal to 0, kappa 0.5, and beta is this initial temperature. So you see here that we have this you see again here for the blue line, you have a stochasticity that appeared here again. Okay, and this is from this yeah, the effect of that. And now if we for T40 here and kappa equal to 0.5 and beta, we have the slope of the phi. This is U temperature U, and this is yeah, this is the temperature in both sides. This is the temperature, and this is the temperature in both situations. Okay, let's see what happens if we consider different values again here. So we are reproducing here. So what we observed here, we noticed that the crystallization of the water droplet in the center of the cylinder. This is the center of the cylinder, and this is the border, right? In the center of the cylinder takes place at practical constant temperatures. When the temperature, stabilization temperature Ts approaches the crystallization temperature of the water droplets, we can notice that the duration of the phase change in the emulsion increase. Okay, so you see here, okay, and you see here. Okay, so this is, we conclude that the kinetic phase changes in emulsion depends significantly on the choice of the temperature Ts, which is the stabilization temperature. What about the conclusions and remarks? So our contribution is proposing a closed to reality stochastic model of crystallization process in a dispersed media by means of stochastic partial differential equations. We proved the existence and uniqueness of this type of equation. We use the finite volume method to solve the direct physical model by Euler-Muriyama in some appropriate functional spaces. We used, of course, the Book-Smaller method to simulate the Brownian motion. All simulation results demonstrated that our model is accurate to the efficient and efficient when compared to the experimental temperature. And for the project or for future works, we expect to use what we call the second order stochastic backward differential equations to describe this model by another approach. And yeah, and then fit the data or the measured temperatures using this backward equations. There is another idea that we also had, or some suggestion in previous discussions, is to consider, for example, a rotating, for example, volume, instead of just you take a cylinder and you consider in a fixed space. What happens if you have a rotating object or another form of the object? So this is our challenging questions concerning this point. The other one is to try to if we can, if the Levy models may have some advantages to describe this type of problem for crystallization effect by supercooling an object in an imbued space. This is the end of my talk. Thank you very much. I just want to keep some time for questions, so I have to stop here.
Wissam, thank you, Dr. Mohammed. Is there some questions? Wissam, you are hearing? Wissam, you are with us or not? Okay. Rafiq?
Yes.
Okay.
Hello. Hello.
Okay. Is there some questions, please? I have a very naive question. When you compare the stochastic model to the deterministic model, okay, and the curve, the stochastic result is, of course, one event. Okay, it's one experiment because it's stochastic. I think there is a noise or something.
Yeah.
It's very naive,
noise,
okay? but
yeah, sure.
Just to understand, huh? Okay.
Yeah. No. Thank you very much for this observation, because when we are saying, okay, we have some stochasticity in the model, and we have made comparison between this and this in the previous one, if you wish. Okay, so now we will see. Okay, but how do you, when you consider stochasticity, how can I observe stochasticity in the model? And so, of course, here to plot things, we can do it in different situations. We can plot many different paths, different trajectories. So we simulate and we obtain the different, of course, at any time you have different realizations or different values, and then you can plot as much as you want, number of curves as much as you want. This is the first thing that you can do. The other one is you can take an average of the 20 curves that you have plotted.
The mean.
And then you will see that, okay, this is the representative of my curves. I take just the average of this to this curve. Or you can take one of them. You can just select randomly one of these curves, and you see this will be the representative of my data.
But if you plot the mean, for example, do you observe that the mean is more regular than one event?
Sure. Yes. The mean is more regular, because with the mean you remove when you take the mean, you remove randomness. You know,
okay.
This becomes like a deterministic model, but by taking all the possible values at different points of each realization.
And is there It's also a very naive question. Is there a deterministic equation for the mean?
Eh, yes, yes, yes. Let me go take a break to the model. But the problem is when we take the mean, the many information are hidden, you know. Let me go to the model. I think this is the model assumption. Yeah, this is the model. The integral equation maybe is better. Let me go to the integral equation. Yeah, this one. So if we take the mean in the equation here, 4, 8, we will have here some deterministic function. We can call it little xt if you want. This one is deterministic, but if we take expectation is not also a matter. This is x naught. And the a expectation here, because this quantity is also, is this one random? Yes, it is random. So we cannot separate here. From here, we cannot separate. So we'll have here a functional term, and this term will cancel out. This term will be cancelled. In fact, to answer to your question, we can obtain an equation when taking the average here. But in order to solve it, we cannot take the expectation inside here. We can take it. We cannot separate here. The only case we can separate this two random variables is when we have independence between u and v. So at that time we can separate, and then we obtain here a linear equation that can be solved very easily. But this is not the case in general. You have dependence between u and phi here. So you have dependence.
Okay.
So this is, yeah. But in fact, we taking the expectation in this equation here, we can have the equation to be satisfied by the expected value. I think that I have seen one of my co-authors in with us. If he wants to make any additional comment or something else, I think Hamu is with us here, right, Hamu? You hear me?
I see him, and
I see him walking, maybe.
yes. Okay. Is there other questions?
He told me that he has a meeting at 6 at the same time where the talk started. Okay. But maybe he finished now, and he tries to, by curiosity, to attend at least to listen to the comments.
Is there other question, please?
Yes, please.
Yes?
Yeah. First, I would like to thank all participants and organizers. I would like to thank Mr. Professor Eddahbi for the clear presentation. My questions is far away of the presentation from your experience, Professor. How to decide which approach should we choose, deterministic or stochastic, to model some nature phenomena? This is the first one. The second one, in the experiment result, damping, maybe it's due to a memory effect, not necessarily a random effect. Thank you.
I'm sorry, there was a problem, there was some noise, and I couldn't really understand very well the question. Can you please repeat slowly the question, first one by one?
Okay, Professor, thank you. From your experience, how to decide which approach we should use, a deterministic approach or a stochastic approach to modeling some nature phenomena? This is my first question.
Okay, let's answer this question first, please.
Thank you.
You said that when, for example, when I am considering a problem, should I choose the deterministic one or the stochastic one? Which one is the best? So here there is some discussion. But for example, if let me just show you, if I can really do it, hopefully. I will share with you my entire screen, and let me just show you something about, for example, so can you see my screen? You are able to see my screen?
Yes, yes.
Okay, so this is the plots of the crude oil prices, right? Okay, so this is if I consider, for example, daily for 1 day, so you have the values here. You see, in this, for example, the price describing this crude oil, you see that you have irregularity in these parts, right? You have irregularity. For example, at this point, the function describing this price is not differentiable. And also you have singularities everywhere. The function is, there is a lot of points here for which the function is not differentiable. So what does this mean? This means that if I want to model this, the problem related to this stock, I cannot use smooth functions. I cannot use regular functions. So, and more for tomorrow, do you know from here, tomorrow, we don't know the price. Is the price going to be above or below? We don't know the future. So everything which is related to the future, we cannot use deterministic models. We cannot use deterministic functions to describe these prices for the future. Another model, if you consider, for example, modeling the, for example, the vaporization of water in a place, for example, in a pool, or of course a pool exposed to the sun, directly to the sun, so you have a vaporization, or you have lakes, for example. If you take any period of time and you measure, for example, the quantity of water that you have in some given volume, so due to the randomness of the media, maybe that due to the temperature, if the temperature is high, there will be evaporation of more particles, of more quantities of water. If it was raining, the quantity of water will become bigger, will become larger. Another thing is the quantity of water that is infiltrated in the deeply in space. Okay, in the area where you have, it depends on the structure you have. So what does this mean? This means that the quantity of water you have in a given volume is changing depending on different parameters of the around you. You have the temperature, okay, if it is raining or not, the structure of the place where you have your lake, for example, or your pool, or yeah, maybe some quantities are going and coming, but you cannot control how much they are upgrading, or how much they increase or how much they decrease. So in this such of situations, you have randomness. So there are many other different. So it depends on the problem you are describing. So you have to describe your model, you put your assumptions, and then you with the modeling with random processes, you have maybe some other flexibility to capture some feature of the phenomenon. So this is somehow the parameters or that guide you, the ideas that guide you to choose the model you are working with. What is the second, please?
Thank you, Professor. The second is that in the experimental data there is a damping. Yes.
Yeah, in the paper, let me go in the experimental. We have let me take you to the first slide, the second slide here. You mean here?
Yes. Yes.
Yeah.
The damping. Maybe it's due to a memory effect, not necessarily a random effect. We know that memory.
Yeah. Okay. It is possible to consider this problem as another different one. From your experience, for example, you say that okay, I have a damping somewhere. Maybe this depends on some memory of the in the problem. Then you can model your problem. But here in this experimental measurement, this heading, it has been explained by the authors that this comes from physical point of view by the interaction between particles. When they became solid, when they became crystallized, their nature, it was transformed from liquid to solid, you know. And when this happened, to make it solid, so particles are heating each others, so there were some compactification of the volume of the surface of the volume that you have of the particles of the water. If you want particles of water, they become solid, and then you have more space. But when there is coalition between particles, there is some heating because of these shocks of these heatings between them. So the temperature becomes a little bit higher, but the maximum amplitude of this variation is 4 degrees only, you know. But this is a physical observation that has been explained by the people who did this work and in the lab. And one of the reasons why we do not consider other models, some people suggest to us, you consider other configuration, but the problem is we compared with this because we have experiment measurement for this. This was the reason.
Thank you, Professor.
No questions? Okay, if there is no other questions, thank you, Dr. Eddahbi, and we hope see you again in our webinar. Thank you, Rafiq. Thank you, Wissam.
Thank you, Professor Mohammed. Thank you.
Thank you to all Nabil, Rafiq, and all others and attendees, participants from over the world.
Okay, see you next time.
After 2 weeks.
Yes.
Bye.
Thank you very much.
Bye.